So as long as, and what is the intensity of this? Let it be anything, that one. So we are not bothered intensity here, that one. Now what I do is I'll make lambda greater than lambda naught, the wavelength of light. Then irrespective of whatever the intensity, there won't be any photoelectric effect. I think this is totally against the wave nature of light, no? This will be totally against the wave nature of light. Second one, so I'll continue here only below. So let me take a surface. And this is a source where the wavelength of source is lambda 2 less than lambda naught. The photons are incident on a surface. Greater than lambda naught. I don't see any photoelectrons. No photoelectric, no photoelectrons will be ejected. Any reason for that? The wavelength is greater than lambda naught. So let's do one thing. Let's talk about the intensity here. Okay? Intensity of source, I1. How you define intensity? Say let's take the 1 watt per meter square. Then what is the intensity of this source also? 1 watt per meter square. No photoelectric effect. No photoelectrons will be ejected. I will, now what I do is I can increase the intensity. How to increase intensity? Bring the source near to the plate. Don't try to change power. Not possible. This is a plate. This is a metal plate. This one. I'll bring the source near to the plate here. Then the photons are incident on it. Then I'll make power 100 watt. Then what is the lambda? Greater than threshold wavelength. Then according to the wave nature, what will happen? Since if you increase the intensity, what will happen? More photons will be incident. No? If N1 photons are incident here, N2 photons will be incident, because we know number of photons are directly proportional to intensity. How to increase intensity? Bring the source near to the plate. Still we see no photoelectric effect. Means, sir, I'll make it this 1000 watt, 10,000 watt. Still you don't see photoelectric effect. But sir, particle, will there be any electron? Yes, there will be electron. That electron will be generated due to heat, not due to photoelectric effect. Because according to the discussion what we made, as the light is incident continuously on a surface, heat will be generated. That heat will be absorbed by the electron. And gradually, what happens? When the energy of electron becomes greater than work function will come out. How many electrons? Very less. Suppose if a 1 lakh, also like a 10 to the power of 10 photons are incident, maybe you may get 10 or 15 electrons. That electrons are generated due to it, not due to photoelectric effect. But you look at this, 1000 watts or 100 watt, it should more photons are incident, so there should be now more photoelectrons. No, when energy of photon is less than the work function, what happens when the energy of photon, threshold wavelength, when energy of photon is less than work function, no photoelectric effect will be seen. Here what happened here? The energy of photon is greater than work function. So therefore those electrons which will interact with photon, they'll have energy more than work function. And what happened with a part of energy they'll utilize to overcome work function, the remaining they'll get ejected. So like this, so what will happen here? The wave nature is unable to explain anything. It fails to explain the photoelectric effect here. So definitely what happen here, when I'm discussing photoelectric effect, what I should discuss in terms of photons here, not the wave nature. So this according to wave nature, nothing called a threshold, no? Nothing called a threshold. There should not be something called a threshold here. For all the wavelength open, there should be a photoelectron. But practically what we see, there's some limit is there. If the wavelength of incident light is greater than lambda naught, then no photoelectric effect will be seen, irrespective of intensity here. And now, sir, here I'll increase the intensity. Tell me what will happen. More photoelectrons will come here. But energy of photoelectron will not change. Means you move the source near to the plate, what will happen? Intensity will increase. More photons will strike. Then more photoelectrons will be ejected. Then what point? Energy of photoelectron will not change. So therefore, by varying intensity, what will happen? Number of photons incident on a metal plate will increase. Number of photons ejected will increase. Are you getting the idea? If a source is brought near to the metal plate, intensity will increase. Number of photons incident on a metal plate will increase. Then more photons will be ejected here. But what happened to kinetic energy of ejected photon? No, that is not depend on intensity here. That depends on work function and energy of the photon. So therefore, if you increase the intensity of source, energy of photon will not change. Number of photons incident on a surface will increase here. So there is a relationship. Number of photons, if you increase intensity, number of photons will change, not energy of photon. If you vary frequency, number of photons will change. No, number of photons will be fixed. Energy of photon will change. I think this is a one crystal clear conclusion is what you have to make it. If you increase intensity, number of photons emitted by source will increase. If you increase frequency, energy of photon will change. So by moving the source near to the plate, will energy of photon will change? No. It's quite clear, no common sense, nothing to do big. So if I move this source here, more photons, what happen will strike the surface. So number of photons are increasing. And what you calculate energy of each photon will be same. How wavelength of light will change by moving source means let's think about practically here. You are near to the tube light. As you go nearer, what happen? The wavelength of light emitted will change. And as you move away from tube light, wavelength of light will change. No. With what wavelength the light should emit, the tube light should emit, it will emit that light, no? And as you move near to the tube light, the intensity will change. The number of photons striking on you will increase. As you move away, number of photons striking on you will decrease. So simplest example, I'm putting this one here. I don't want to put anything mathematics here. That one very practical thing. If you move near to the tube light, number of photons striking you what on you will increase. If you move away, number of photons striking on you will decrease. So what happened to the wavelength of light emitted by tube light? If you move towards it or away, will not change, no? And the energy of photon depends on what? Wavelength of light. So this is the thing. Energy of photon depends on wavelength of light. Number of photons depends on intensity of light. This is the thing. So according to wave nature, so irrespective of wavelength or pen, here also I should get photoelectric effect, no? Because what happened? The light is incident. In fact, here more energy, no? See, 1 watt. If you want, I'll make it 10 to power of 6 watt. 10 to power of 6, I'll make it. Then also I see no photon. But sir, like this is something very high energy, no? Okay. Now what happened here? You look at the wavefront. The wavefront will go in incident on a metal surface. Then a given electron, what happen? The energy in a wavefront, what happen? Will not be incident on one electron. Because if this is a wavefront, then in this what happen? There will be millions of electrons. So the energy in one wavefront what happen? Will be absorbed by all these electrons. Then energy gained by one electron will be very less. This is what happens in wave nature. So therefore, the wave nature fails to explain the photoelectric effect. Just give some time. Okay, come. So therefore, what we can conclude here, the wave nature is unable to explain the photoelectric effect phenomena. So what we should do, we should go for the particle nature of light here. So therefore, the threshold wavelength is brought into picture. I just gave one very best example here. Account to wave nature is what I solved it. I got after what time the electron will be ejected after this much of time. And now we'll calculate energy of photon. You calculate energy of photon, how much it is. In fact, it's greater than work function. You calculate this energy of photon. I think energy of photon. Let's see that. Because some of you are asking this question, so let me clarify this also. Energy of incident photon is 2 point. Some of you are asking in this way. I'll give explanation for this also. This is energy of incident photon. No, sir, since energy of incident photon is less than the work function, that's why it took time. Now you do one thing, you take surface, you take a this surface, metal surface of work function 2 electron volt. In that case, what an energy of incident photon 2.4, it will be greater than work function. In that case, what happen? Just it will become half of this. Able to analyze. Energy of photon is this much. Huh? What is the energy of this metals work function of metal surface? 4 electron volts. Since like energy of photon less than work function, that's why it is taking more time. We'll do one thing. We'll take the work function of this metal surface. Let it be 2 electron volt. In that case, how much it will become? It will become half of it. How much it will be? 28.4. Then also what will happen? Though energy of photon greater than work function, still what happen? According to wave nature, it should it will take some time here. So according to wave nature, the photoelectric effect is not instantaneous, but practically what happen? It's instantaneous. So therefore, something the way we are thinking itself is wrong. We should not treat a light like a wave. Able to make it out? You can do this problem for. I'll just change it. So let this be. I'll make it 2 electron volt. Then if I solve it, I'll end up with this. How much? 28.4. Now look at the energy of photon, greater than work function, but still what pen it is taking this much of time. But we know it's a 10 to the power of minus 8 seconds. So what it shows now, the wave nature of light should not be taken. Can you hear me now? Can you hear me clearly?
Yes, sir.
Yes, sir.
So you should not take the wave nature to explain the photoelectric effect. I took 4 electron volt. Now if I change 2 electron volt, I'll make it 5, you make it 1, but altogether what it shows, there's a time delay. But we know photoelectric effect, it what happen is an instantaneous process. There's a time delay. So this shows that, the wave nature of light fails to explain the photoelectric. Then one more, we have a threshold wavelength here. If the wavelength of incident light less than threshold wavelength, irrespective of intensity, what will happen? We'll get a photoelectric effect. Okay, got this? If the wavelength of light is greater than threshold wavelength, no photoelectric effect, irrespective of wavelength here. Means here such a high intensity, more number of photons, but the energy of photon is less than work function. What happen? Any photon that is incident which will interact with electron, those electrons what happen? They'll encounter collision. By the time they arrive at surface, their energy will be less than work function. So therefore, they fail to come out here. But practically, if you see that after 1 hour or after an hour or after 2 minutes, few electrons will come out. That will come out due to what will happen? Due to thermal agitation, not due to photoelectric effect here. So this shows that we should not discuss the wave nature, we should discuss the particle nature. This is what Einstein, so earlier, the Hertz, Heinrich, okay, there were many scientists what happened, they were able to explain all this, and they were unable to explain that why wave nature we are unable to explain here. So by this time, because the reason is YDSC. In 1850s, what happened? The YDSC, the Young's what happened, demonstrated that wave nature of light. From 1850 to almost till 19th century, the wave nature of light dominated the physics. And with the help of wave nature, they wanted to explain. But practically, the things were different. According to theory, what will happen? The wave nature, what happened, was unable to explain. But practically, we got totally different answer. Again, you do YD experiment, it's the wave nature only we are able to explain. But the same wave nature failed to explain the photoelectric effect here. So finally, what happened? The Einstein proposed the wave what happened is also having a particle nature. So rather than calling the particles, he gave name photons. And the same thing I think Newton assumed long back. No, he said corpuscles, the light corpuscles, corpuscular theory. That one, that corpuscles only what happened. The Einstein called it as a photons here. So now what happened? The light will behave like a particle. That one. So like this here, the dual nature of light came into picture. We should not say wave nature is wrong. In YDSC, particle nature. No, the light there will behave like a wave. Here, when the light is incident on a metal, any metal surface, here the light will behave like a particle here. So the due nature of light will come. So it all depends upon the the situation. So how do I come to know what situation? Okay, you do one thing, you assume anything. and if practical and theoretical ideas are not matching, so there's some problem with your the assumptions what you're doing. So switch over to other theory. So whenever it comes light, what happen? We have two ways of expressing the behavior of light, either particle nature or the wave nature. So when to take wave nature, when to take particle nature is what all those experiments are there. So photoelectric effect will not support the wave nature of it. The reason for that, according to wave nature, photoelectric effect is not instantaneous, but practically photoelectric effect is instantaneous. The moment if I make some light incident, I see electrons are ejected within a fraction of time. But according to wave nature, it takes large amount of time. Then next again, I got a threshold wavelength. This I can do practically. I'll pick up some wavelength greater than lambda naught. Then irrespective of intensity, I don't see any photoelectrons ejected here. So this is against the wave nature. No? So these two things open are not supporting the wave nature. Particle nature is it's very quite easy that one. With the help of particle nature, we can assume that why here no photoelectrons. The energy of photon is less than, I'll just put it in simplest way. The energy of photon is less than work function. That's why no photoelectric effect. The energy of photon less than work function, no photoelectric effect. What happens to number of photons? Is number of photons are more here, but still what happens? The energy of photon is less than work function. So therefore, no photoelectric effect here. So what is the conclusion here? How to vary intensity? Move the source near to the metal plate. Intensity will increase. Number of photons incident on metal plate will increase. If you move the source away from the metal plate, intensity will decrease. Number of photons incident on metal plate will decrease. So by moving the source, energy of photon will not change. By varying wavelength, energy of photon will change. So therefore, by varying frequency, energy of photon changes. By varying intensity, number of photons changes. This is a conclusion what we have here, that one. Okay, tomorrow we'll take the experiment, that one. This is about the theoretical background. Just go through once, read. Tomorrow we'll continue from here. Okay, thank you all of you.